The second speaker is Malcolm MacIver. He's an associate professor in mechanical and biomedical engineering at Northwestern. He has pioneered, he has been able to bring really two different things to bear on some question, like how certain fish sense environment and connecting that with robotics. He also developed science-inspired art installations, has exhibited them internationally, and what will give him credibility about making predictions about the future, he has consulted for Hollywood in television and movies, including Battlestar Galactica, the prequel Caprica, Tron, Superman, and Man of Steel, and has been a blogger for Discover magazine. I'll give you Malcolm MacIver.
Well, thank you very much, Tino, and thank you to the Chicago Council on Science and Technology for this opportunity to talk about what I think is really an extremely important issue, the future of work. I'd say it ranks only second to climate change in terms of its importance for society. Like my predecessors, the superorganism I will refer to as Chris Larry, I'm going to start off with a popular culture reference. This is a shot from Wall-E from 2008, envisaging the future of leisure once all the computers and robots have taken over work. Here, videos Skyping to one another. Science fiction is always an excellent place to sort of see where people's anxieties and hopes about the future of technology are, and this is, I guess, either a utopia or a dystopia, depending on your feelings about Barca loungers. If you combine, though, the current statistics on obesity and the sales of this gadget here, it looks like the future has already arrived for at least some of us. Of course, this is a probably more positive take on what's going to happen. I've, as Tino mentioned, I've consulted for a few different movies, including Caprica and this upcoming version of Terminator Genesis, where the vision is really one of robots and computers taking over and then extinguishing humans via nukes. So positive and negative feelings about where technology is going to take us. I'm going to start off with a little bit of a context for some telling you about the work we do in the Neuroscience and Robotics Laboratory at Northwestern. I'm one of 6 faculty there. So this is a shot from 2010. You'll remember these images from the Deepwater Horizon disaster. Of course, it wasn't a failure of robots that caused the disaster in the first place, but the fact that it took 86 days to cap the well is really a failure of robotics. The main workhorse of that industry is this device, the remotely operated vehicle. It's tethered to the surface. It carries about 10 microwave ovens of power down and sends signals up. You've got most of that power actually going into these very powerful lights and some thrusters, hard to see here. And here's the problem. So every time they move the ROVs near the floor of the ocean, this is what would happen. You blow up a tremendous amount of silt. You can't do anything for a considerable amount of time as you wait for the silt to settle. And then you can go ahead and try to do another operation on the wellhead. So a few problems then. One is that we rely exclusively on vision-based systems using high-power lights that don't function well in turbid conditions and murky conditions such as these and such as other situations like search and rescue of a sunken ship. And secondly, a cause of much of that disturbance is these powerful thrusters that send very focused jets of fluid around and disturb the substrate. So besides that problem context, there's of course many others. Search and rescue in freshwater conditions, extremely murky. These divers do extremely dangerous work and feel around with their hands essentially, including having to do that inside of, in this case, the Costa Concordia. So there's many situations in which we need systems that will do better without visually guided task operation. So here's the animal we've been working on for the past couple of decades in my lab. It's a weakly electric black ghost knifefish from the Amazon. It's one of 200 species that work in a very different way from the kinds of animals you're used to. That's a signature of that different way is that it doesn't have a big tail that it flaps from side to side to propel itself. It rather uses this fin. You'll see a shot of that in a video in a second. And at the other end of the body, you see these very tiny eyes. And the reason for that is that it doesn't use them for its everyday getting around and finding its meal. It basically hunts at night, but in rivers that look like this. As soon as you put your hand in, it disappears. You can't see anything. So even if you had the best eyes in the world, it would do you no good. So fast-flowing, super murky, high current conditions. There's actually no robot we have that will work well in this kind of environment. They've been doing it for 100 million years quite nicely. And what's really amazing is that this is really what its environment is like, because as I said, they're nocturnal. So they hunt in complete darkness. How do they do this? Well, a couple of different things. One is they use this incredibly high agility system. They're able to ripple their fin in many different ways to get all kinds of different directions of movement. They often swim backwards. There's no real advantage to swimming forwards if you're not using eyes to look forward. So it often swims forward, it swims up, it hovers, it does all kinds of cool tricks mechanically that make it a fascinating subject from the standpoint of robotics. And here is a robotic implementation we built for a whole bunch of scientific sort of work that I'll only be able to touch on briefly. There it is swimming in a water treadmill. It's suspended here from air bearings, and it's swimming at a good clip there. So with this robot, we've uncovered a lot of secrets of animal agility. One of the odd things we recently discovered that's PNAS is that animals, including ourselves, simultaneously can achieve stability and agility by activating agonist and antagonist muscles at the same time. So you do that actually every time you're trying to put something very precisely into a hole in the wall. You'll contract your bicep and your tricep at the same time as you're doing a precision grip and trying to position your arm very precisely. And we've sort of uncovered the mathematics of this and published this recently based on work that we've done with fish, because they actually do the same thing with those waves that you saw along the fin. They send two waves in opposite directions, fighting itself, it seems, but this gives it really great agility that we've demonstrated using our robot and implementing it on our robot. So on the other hand, so that was movement. On the other hand, lights and all the power needed for lights is a huge problem. So we've developed an artificial version of the way the animal senses. It uses 1/200th of the power of a single light bulb as opposed to 10 microwave ovens of power. And it uses, it generates a field using electrodes at either end of the body and picks up distortions. And we've learned a lot about signal processing from the fish that I don't have time to go into, but we've integrated that into boards. And the essential principle, just so you understand some of the physics of this, is if you have an object, for example, an insulator, and you have a field being sent out by this pod, as the field goes by, if we look at the voltage difference between A and B, you see there's this tiny fluctuation. So the animal has 15,000 of those sensors and reconstructs a picture of the world in order to hunt and navigate and do all the tricks that it does using that very interesting sensory modality. So we've implemented a variety of algorithms using this sensing technique. And here's an example of it working in a pylon maze. And so the way this experiment works is that the sensors are doing all the processing, taking in the signal and doing all the processing on board here, and then sending position control commands up to here. No human in the loop. The only thing we have is we're telling it to go from one end of the tank to the other. That's the only part of this that we're telling it to do. But otherwise, it has to figure out its own way through this pylon maze. Let me see if I can get you some audio. So the VU meter on the left and right are showing you the relative intensity of the field distortion on the left and right sides of the robot that it's using to dynamically guide itself through the maze. You could adjust those pylons in real time and it would find its own way through this clutter. Now what's fun is you can use this very high technology device called a flour sifter to add a little bit of dirt to the water and rerun the experiment. There's absolutely, of course, no change in performance. Now, interestingly, there's no competing sensor in industry that will do this kind of task with this kind of close clutter. Sonar won't work. Obviously, vision won't work. Ultra shortwave sonar has all kinds of backscatter problems with clutter this close. So we've deployed, recently we've put our sensor pods on a conventional ROV, and we're just about to do experiments in the pool at Northwestern and Lake Michigan eventually, and then hopefully hand off this technology to industry to help in situations where it's really needed. Now, a little bit of update, what we're currently working on. This is a new model of our robot which has no strings attached. It's going to be able to swim autonomously. And this is a really exciting machine for us. It has 66 what's called degrees of freedom. This is a figure of merit for robots. It's a really simple concept. This is 1 degree of freedom. Here's another degree of freedom. So it's basically how many different ways a robot can move. And all that is packed into a volume of 3.5 cups of water. So this is our current design. We're about to embark in building this with collaborators HDT Global Robotics, as well as funded by the Office of Naval Research. And by the way, here's a penny, I should say a dime, for a sense of scale. And in comparison, the Honda ASIMO has 57 degrees of freedom in a volume that's more than 100 times the volume of the robot I just showed you. So it's really compressing a lot down. It's taken a lot to get there. We're actually using the smallest bearings commercially available. Here's a penny, and it's a little bit bigger than Abe's eye there. And motors, here's a dime, that are also very tiny, made by Maxon, the company that built the motors that are in the current Mars rovers. And we've been working closely with them to get the right specs on this. So this is a design now that we're building and will hopefully get done in the next 6 to 12 months and be able to do a whole lot of really interesting science.